chromatic numbers of stable graphs. And he's indicated that if you want to Zoom people on the Zoom, if they want to unmute and ask a question and interrupt him, he's okay with that. But otherwise, I'll be keeping track of the chat as well and can intervene that way.
Okay, yeah. So thank you so much for the invitation. As Achim said, it's about chromatic numbers of stable graphs. And I should state it's joint work with Itai Kaplan and Saron Shelach. Okay. Something has to go ahead.
Press and hold the big button.
Yes. Oh, hold it.
Press and hold the big button. And then now press again.
How long should I hold it? Yeah, okay, I'll just do it this way. Okay. Oh, what? Doesn't move. Ah, good, thank you. Okay. Okay, so some preliminaries. So a graph is a set together with symmetric reflexive relation, or just PE. And the coloring of the vertices is a map that assigns each vertex color, say of size kappa and var kappa, such that if two vertices are connected by an edge, we want them to be colored by different colors. And the chromatic number of a graph is the minimal cardinality of such a vertex coloring. Of course, such a coloring exists. You can just color each vertex by a different color, but somehow you want to figure out what's the minimal cardinality. Okay. Good. Okay. So this will be the main example for us of a graph. So I believe there are other graphs in the world, but it will be the shift graph. So let kappa be any cardinal and be an integer. So we color increasing n tuples of ordinals less than kappa. So, okay, I don't have n fingers, but let's say 4. And we want to say either, okay, I don't know if you can see me. Either this happens or the other way. Okay, so you shift it by 1. So either S1 is equal to T0, S2 is equal to T1, and so forth, or you go the other direction. So you color the tuples and you say the two tuples are connected by an edge if there are a shift of one to the other. Sorry? Yes, so S1 is equal to T0 and S2 is equal to T1. Yeah, so maybe I should have drawn here 2 lines and then it will be clear. Yeah, exactly. It's a simple application of Erdős-Schroeder that if you take kappa large enough, you can get any high enough chromatic number as you want. Okay. I mean, the fact that you use Erdős-Schroeder is almost implicit by how it's phrased. Okay, good. So yeah. So there are a lot of works, I think, starting with Erdős, about what kind of properties or what kind of somehow things you can say about graphs with uncountable chromatic number. For instance, I think you can embed into them any finite bipartite graph, and you can embed any finite even. No, yes, any bipartite graph. So you can embed any even circuit, and you can embed also any odd circuit with large enough odd circuit. So there were a lot of questions like this going around, and Taylor, who's actually, it's in his paper on logic, asks the following: say you have a graph G, which has uncountable chromatic number, and any cardinal kappa. So does there exist a graph H with chromatic number larger than kappa or equal to kappa, such that G and H share the same finite subgraphs. So actually, he didn't really phrase it like this. He phrased it as, okay, aleph1, he didn't write aleph1, he just say, does there exist, and what is the minimal mu such that this would be true? So the fact that such a mu exists is some kind of general Hanf number argument. And the fact that it's not aleph 0, you can find a counterexample. They exist. So somehow the conjecture settled into the following conjecture. Not long after, Taylor and independently Erdős, Heinal, and Schellach asked the following conjecture, which is somehow similar. Say you have a graph G, which has uncountable chromatic number, and can you find a natural number n so that G contains all finite subgraphs of the shift graph that we had before? So is the fact that you can find a graph that has very large chromatic number, is it due to this very weird looking graph? Is it his fault? So it's not hard to see that really the strong implies the regular, right? Because if you can find all finite, then you can, of course, take an elementary extension and then find the shift graph itself, or take even a larger elementary extension and find any shift graph that you want on any kappa. And then, of course, you can somehow. Oh, regular is just this one. Yes, without the strong is regular. Yeah.
So by a subgraph, you mean induced subgraph or just subgraph? I mean, there's this.
No, just subgraph.
Okay, thanks.
Yeah.
There's also a question on the chat whether G should have other finite subgraphs besides the ones in the shift.
Yes, of course. Yes, yes. It can. All we care about what is the real reason that it has an uncountable chromatic number. So in order to have somebody to blame, you just need to find certain configurations. We don't care if there are other vertices, right? Okay, so what do we know about these conjectures? So first, the Taylor's conjecture is consistently false. Okay, there is a model of set theory in which it doesn't hold. It could be, but it's also consistently true. It's also consistently true if you switch the aleph1 to aleph2. So right now the aleph1 part is open. Okay, you can say, okay, fine. Then we don't know about this. What about the strong conjecture, right? It was refuted. Even I think a couple of years after it was conjectured by Heinal and Comyas. Okay, so this is the 6th slide, and maybe you can say, okay, that's good, we can go, right? But maybe there is a bit more to say. So this is where model theory enters for us, because we know that model theory, at least classification theory, is a lot of the time about what kind of graph relations you don't allow to be embedded into certain formulas, right? So there is some connection. So this is our theorem. Myself, Itai Kaplan, Saron, Schellach. First, that if G is omega stable, it's an omega stable graph, then the strong conjecture holds. Okay, so the one that we stated before, that if your chromatic number is greater or equal to aleph1, then you can always embed all the finite subgraphs of the shift graph. Okay, we know it for omega stable. What about a little bit higher in the hierarchy? If G is super stable, then we don't know about the strong conjecture as I stated it, but we do know that if you replace it with 2 to the aleph 0, then we're still okay. So what's next? Stable, right? If G is stable, then the strong conjecture holds, but this time we need to go to bet 2. Okay, okay, we don't know if we need to. That's what we were able to prove. Okay. So we proved this in 2 papers. In the first, we proved 1 and 2 and a version of 3, which was not for any stable graph, but only for stable graphs interpretable in a stationary stable theory. And that a stationary stable theory is the one that every type is stationary over anything. Okay. And then I guess a natural question is, can you always interpret any stable theory inside a stationary stable one? And Udi gave us a counterexample, just ACS. There is an argument, actually a very nice argument.
What's the question again?
If you can embed any stable theory inside a stationary stable one. And not interpret, sorry, interpret. Yeah. And you can't do it, you can't even actually do it for any, say it's positive characteristics and any P closed. Yeah. Basically because you have different roots, and then you have to choose somehow, right? Yeah. Okay, so we needed to, so once we knew this, we knew we needed to have another paper, another result. And that's the second paper. And it's almost the proof is somewhat similar to the proofs that we did for 1 and 2, but it required some different tools. Maybe some examples for omega stable, super stable, and stable graphs. Then for omega stable, okay, the problem, right, with the shift graph is that we had an order, and then somehow it's how do you talk about the order in stable theories? But you can take the symmetric version, in which you don't care about increasing tuples, but only any tuples, and have the same edge relation. That's omega stable. For super stable, it is known that every ultra flat, which I don't remember the definition, but every planar implies it, so any planar graph is super stable. And for stable graphs, we know it for super flat graphs, which again, I don't recall the exact definition, but there are plenty examples of such graphs. Okay. So these papers are divided into two, the model theoretic part, and after we have some model theoretic machinery, then it's basically combinatorics. So let's talk first about the model theoretic part. So the key model theoretic part of the proofs is that every sufficiently saturated, allowed saturated extension is an EM model. So what do I mean by that? So let's give some kind of hint wavy definition. So maybe you should, yeah, okay. So what is an EM model? So here is okay. So I'm guessing I have some until here or something, but yeah, okay. So say with your language, okay, with column functions. Sorry? Yeah, L, T with column functions, then an EM model is the definable closure of an indiscernible sequence. Okay, so it turns out that for omega stable and for super stable theories, every large enough saturated model is exactly that. You can find a column expansion, or that's probably this column, any column expansion would do. And you can always find an indiscernible sequence such that your model is the definable closure of an indiscernible sequence.
Indiscernible in the new theory.
Sorry?
Indiscernible in the expansion.
Yes, I mean, yes. And so these results go back to Lascar, and they were shown by Mario for omega stable and for super stable as well in his thesis, and later by Sherlock as well. And you can say, okay, so we know it for super stable and omega stable, maybe it's true for stable theories as well. And it turns out it isn't. You can show that if somehow you want to control your language and you don't want to expand your language too much, then such a result would necessarily imply superstability. So we need to look, we need to somehow generalize this picture. And how do we do that? Okay, so note that here every element in the EM model is of the form, okay, you have some kind of definable function, and then you plug in a sequence, right? Your indiscernible sequence. Then every element can be indexed by two indices. One goes over all your theory, I mean, all the definable functions, and finite sequences. So maybe you can generalize this. So we take infinitary EM models are models that each element can be indexed by 2. Now, okay, so assume the theory is countable, okay, just to, okay, I don't know if you can see this. Okay, and I it will be smaller than 2, say 2 to the aleph 1, and eta would be a sequence, an increasing sequence, of length less than aleph 1. Okay, so instead of only allowing finite sequences, we now allow infinite sequences, but now we forget about the definable functions. Somehow the regular EM models came from definable functions, taking definable closure of indeterminate sequences. Now we forget about that, and we only care about that every element can be indexed by two things. One, we think of what is the definable function that gave you this element, but it's only an index. And the other index is an infinite sequence. So it's still not enough, right? Because we somehow need to remember the fact that this has to be indiscernible somehow. So as I promised, hand-wavy definition, every time we fix an I and we let the eta change, we want it to have the same type, but only for tuples as well. Okay, so it's hand-wavy, but somehow gives you the sense of what exactly we're generalizing here.
So it's an abstract indexing.
Yes, abstract index.
Elements of the thing by this data.
Right. Yeah, because now we're allowing infinite sequences, somehow you can't really. Yeah. Oh, and we showed that yeah, of course, we showed that every stable theory, for any stable theory, every large enough saturated model is exactly of these four. And basically, there's an equivalence. If you have a theory such that every large enough saturated model is of this form, then actually it's stable. Okay, so let's give a very rough outline of the proof, and the proofs are somehow similar. Okay. When did we start?
We started a couple minutes late, so you have 10 minutes.
Oh, 10 minutes. Okay, good. So assume we have a graph with that the chromatic number is larger than beta 2 to aleph 0. Okay, so assume we're in the stable case. Okay, first we find a saturated extension such that it's an infinitary EM model, so of this form. We can do that. Now we, like Anand said, we only care about the indices. Okay, we don't care about the elements. So we have a map sending this pair into its element, right? It's a surjective map. We can use this map to induce a graph structure on this pair of elements, such that any two are connected if and only if their image is connected. It's a homomorphism of graphs. And you can also show that the induced graph on this B also has this large chromatic number. Oh, yeah. But then you can say, okay, but say we can embed all finite shift graphs of some shift graph here. Why does it mean that we can embed it here, right? I mean, it's only a surjection. It's not injective even. Okay, so that's already a result from the first paper that actually it's enough. And that if you can do it for, if you have a map, a homomorphism of graphs, and you can do it for H, you can also do it for G, but maybe you need to change your N, but this doesn't matter. Okay, now we have our graph, and you can partition it by looking at different, by partition the vertex set by looking at different eyes that you have. because our chromatic number is pretty large, we can find one of the partitions that will also have a very large chromatic number. And now forget about I, and we only care about infinite sequences. So this is already starting to be very combinatorial, because now we only have a graph about infinite sequences. But we don't know anything about the edge relation. This is where indiscernibility enters into play. We now have two infinite sequences. We can look at the order type. Okay, this element is greater than this one, this element is equal to this one, and so forth. And we can now partition not the vertices, but we can partition the edges by means of the order type. The order type, I mean, we only have a bounded number of order types around. So we can also show that because we have that large chromatic number, that actually there is one partition of the edges such that it is to blame that we have this high chromatic number. And now it is a purely combinatorial question. We have a graph on infinite sequences, and we know exactly what is the edge relation. The edge relation is our two sequences are connected by an edge if and only if they have a certain order type. And now this question is, once we have this graph, can we embed every finite subgraph of the shift graph? And this is the main theorem. I mean, up until this point, it's only a few pages in the paper, and this is the main theorem, that we can actually do it. And it's a very sophisticated combinatorial, I mean, not sophisticated, I mean, it's very technical. I mean, it's pretty technical. And okay, and in the first paper for the omega stable and superstable, we didn't really need to consider this order type because these sequences were finite, because we used regular EM models. And once they are finite, everything is much easier. But once you're infinite, then if you look at the order types, things can get pretty messy. Questions? Yeah, okay. Okay, so further directions. So first, what about other things other than stability? So a first natural direction is simplicity. And why is that? Probably because, probably most of you know it, or probably all of you know it. There's a deep connection between stability and the saturation spectrum, right? I mean, one really gives the other. And we didn't really use saturation. If you're a bit careful, then we didn't really use saturation. I only cared about the fact that I can embed my graph into this EM model. So I really only cared about universality. Saron has this plan, I don't know where he is progressing about it, that maybe there's some way to describe simplicity using the universality spectrum, as was done for stable theories. And if so, probably it's a good direction. For NIP, we have nothing. I mean, we have some results for simplicity, but it's still very rough. Another direction is maybe have better and more precise bounds on things that we found. For example, on the N, we could embed a shift graph, all finite subgraphs of a shift graph into our graph for a certain N. What can we say about this N? And I'll say a bit more about this in a second. And more importantly, what about the bet 2 of Aleph 0? The fact that we proved this doesn't mean that the strong conjecture isn't true outright for stable theories. We don't have a counterexample. Just this is what we were able to prove. And regarding this N, then we have a theorem started a long time ago together with Elad Levy, that if in an omega stable graph with countable chromatic number, if the U rank is very small, as in great M less than or equal to 2, then we can embed all finite subgraphs of the shift graph when N is less than or equal to 2. So maybe there is a connection. I mean, we tried to prove this in some kind of inductive way, or at least phrase it in some kind of inductive way, but we didn't really see a way to do it for higher U ranks, but maybe there is a way. Maybe there is a connection. Thank you.
Thank you, Yatir. We'll take questions, but I did miss one of the questions.